and kind of learn how the system is architected and how we put everything together and stuff like that, which is going to be pretty cool. So what I wanted to do today is show you how to build a simple 1-bit ALU and to get used to the Logisim environment. What we're going to start off with is some basics. Up here in the corner, you have a couple of tools. You've got the pointer tool. This is our simulation and interaction tool. That's what gives us the little finger. We've got the design tool, which is the arrow that allows us to select devices and put them onto the world, into the simulation environment, and to make designs. And we have a text tool that allows us to do little labels and stuff like that. We're going to be mostly using the design tool and interacting with it using the interaction tool. So let's go to the design tool, and the first thing we're going to do is place a simple logic gate to see how everything works. Right? So up here you've got your basics, you've got not, and or, but you've also got a whole list of other gates down here in the gates menu on the side. And this is your library over here. This is all of the things that are available to you that Logisim gives you by nature. And we're going to be building some tools into the library as we go. So I'm just going to select the AND gate, and I'm going to place one of those. And now that you can see, I've placed the AND gate, and over here on the left you've got all these little blue dots. And these blue dots are our inputs, the red dots are our outputs. And they're blue because they're disconnected. When they're connected properly to an input or an output, they'll go either kind of a light green or a dark green. And that'll tell us whether they're activated or not. And you'll see that in a second. Down here we've got the properties of the gate, or whatever the device is that's selected. In this case it's facing east, and I can use the arrow keys. If I press up, it makes it point up. If I press left, it makes it point left, and so on. I'm going to make it point right, like normal. Data bits tells us how many each of the inputs operates on. So in this case, if I changed it to say 3 data bits, these the blue dots change to black dots, and each one of those is 3 bits. So I can AND 3 bits together all at once, which is pretty cool. We're going to stick with 1 bit at a time. I can change the gate size from medium to narrow, which is a tiny version, and you can see it spins out there, and I'm going to keep the narrow version. And I can choose the number of inputs. In this case, it's an AND gate that ANDs together 5 inputs all at once. I only need 2, so I'm going to pick 2 from the list, and now it looks more like our normal AND gate. I've got 2 inputs and 1 output. I can also give it a label, and I can change the font of how it looks and stuff like that, but I don't really need to right now. Next, I'm going to show you some inputs. So the inputs are one type of pin. So we've got 2 types of pins. We've got an input pin, which is square, and we've got outputs, which have rounded edges. Right? So here I've got an output, and I've got an input, and I'm going to add one more input here. And then we can start wiring these up. So now that I'm in the design tool still, I just pick on one of the pin connections and drag it over. And you can see that it just makes the connections automatically. And as I keep adding them, things change from blue or red to green. And that tells me that I've got a valid data path, right? Then I can switch to the interaction view, and I can start playing with this thing. So I can actually turn each of these on and off. And when I click on it, it turns from 0 to 1, which makes the line go from dark green, which indicates a 0, to light green, which indicates a 1. And you can see when I click both of them together, we get the regular AND output. If both of them are not activated, the output is not activated. And this output will tell us all kinds of stuff too, which is super cool, right? So we're going to build an ALU for the MIPS processor using this process. So here we've got our basic AND, and we want to add these other operations too. We've got OR, XOR, NOR, and add sub. So these are the things that we want our ALU to do. We're also going to do a less than operation that we looked at before in class. So to make those, we're just going to start putting down these gates. And finally, I'm going to put down an adder. The adder is under the arithmetic block, and there's a very basic adder, and we're going to be adding just 2 bits at a time. So it's a 1-bit adder. And I'll drop that right here. And you can see it's got a carry in inputs, it's got a carry out output, a 1-bit output, and 2 inputs here, right? So now I've got my inputs, and I need to wire them up so that they're connected to all these things simultaneously. So this is going to be my A input, and I can go here to my label and make this my B input. And if you want to change where the label location is, you can put it on the bottom, or you can put it on the top, or I'm going to keep it on the west side there, and I'm going to pull these out so we can make nice clean connections to all the other items on the list here, right? So I'm going to go through, and we're going to connect each one of these. I'm going to connect all the A's to the same location, to the top inputs of these gates, and then I'm going to connect all the B's just like that, right? And this is my output. I'm going to call it result. Awesome. I'm going to pull it over here. Now the problem is that I've got all these outputs, and I need to combine them all together so that they share one result. So what I'm going to use is a multiplexer. And we are going to, under here, under the plexers folder, there is a multiplexer option. We've got 1, 2, 3, 4, 5 operations plus the less than operation, which means I have 6 operations, which means that I need 3 select bits to capture 6 operations. I'm going to do 1 data bit at a time, which is totally cool, and I'm going to put my select location on the bottom left, on the top right. All right, so here's my mux. This is the select location. I'm going to not include the enable. This is the selector right here, and then I've got my various inputs and the single output. So I'm going to delete this wire, and I'm going to put these guys right here, put my result over there, and I like to line up the very top one just like that and wire these guys up like so. And I connect my result here, and it's still blue because I don't have a selector. So the selector, what's going to happen is I'm going to add another input, a multi-bit input, that we're going to use to choose which of the operations to execute. So I'm going to add an input here, and I made it face down by pressing down, and you can see there's an incompatible width. This means that this is a 1-bit input, and it needs a 3-bit input on this side. So to make this go away, I change the number of data bits from 1 to 3. That makes it a 3-bit input. You see it's still got squares, and if you look, when we run it, you can actually see it change. So this is selecting the OR, and if I make that go away, it switches those. And you notice the AND isn't changing, but the OR is, and that's causing that to change, which is pretty cool. And when we select the ones that are higher, we're selecting ones that are not connected, and that gives us a little error. So we try to avoid that. So that's our mux. That allows us to select the operation. We also need to make sure we connect, to get the adder to work properly, we need to connect a CIN. So the CIN is going to be pretty handy. We're going to do one of those. We're going to put it up here, CIN. I'm going to put it on the north. So that gives us a straight up adder, but we also want to do a subtraction, right? Because right now, if I select, let's see, that's 0, 1, 2, 3, 4. If I select 4, right? If I select 4 and I add them together, you can see I've got A plus B, and that's 0, and I've got to carry out. I want to make sure that I carry out as well, because we want to make sure that that works properly so that we can use this with the next one. Make it point up, call it my mouse keeps wanting to drift off of the thing. See out. I want it to be on the south side. There we go. So I can add, but I can't subtract, which is a problem. So to make it subtract, we know that we just put an XOR on the front of the B input and add a add sub signal, because the XOR basically inverts B 2's complement representation. We just run B over here, so this is my B signal. I run it around to the XOR, and I'm going to add a second input. Right? So now, when we're interacting, if I want to subtract B from A, I hit the sub signal that inverts it, and I want to make sure I carry in 1 because that gives us the proper value. So that's our add sub. So this changes our regular add to a sub by doing that, and I want to make sure I don't carry in when I'm adding. So now I've got my basic mathematical operations. We also want to support comparison, and the comparison is another input. We're calling it less. So we're going to add another input here, and that's going to be our 5th operation, our 6th operation, right? And this is just a pass-through, and you'll see how we use it when we build up the whole ALU. Are almost finished. As part of the less than operation, we also have to break out a set output. So I'm going to have a last output here, and this is called set, and put it south. So this is our basic ALU. We've used multiplexers, we've done outputs, and we've got 6 operations, including a less than operator that we'll use later that supports our set less than operation and stuff like that. And now I'm going to set it clear all of these. And we can capture this as a overall object, right? So the way that we do that is we switch. So here you've got the different modes. You've got a hierarchy mode, that's the simulation hierarchy. We've got the circuit layout, which is our design environment, but we also have the object view. And what this is a view of how the inputs and outputs are oriented on a little box. So we can actually treat that whole design, if we go back to this view, we can treat this whole design as one object, which is really cool, and we do it very simply. So when we switch to this view, we can see which ones of these are activated in a little window that shows up down in the corner. You can see them show up over here. So this one is our multiplexer input, this one is our CN, this is the sub, this is A, this is B, this is less, this is C out, this is set, and this is R, right? But we can't tell from the outside, so we want to label it, right? So we're going to spread this out a whole lot and move this guy. So that's an anchor, and you can see they only go onto dots. We should probably have enough room if I put them there, and that's the actual output. And we can move the outline back where it should be. And I want to put my select. So this is, I'm going to use the text tool, or operation input, so that tells us which operation we're doing. Then I want to move my, this is CN, I believe. And we just want to move these around until they're arranged well. So I've just gone and arranged and the outline around so that none of the labels overlap, and it's really easy to see which label is which and things like that. And now I'm going to label the whole device as a whole, and I'm going to call it 1-bit ALU, just like that. Right, so this is our 1-bit ALU. It's very simple and very useful. And I'm going to rename over here. This is the actual object that I'm working on. So I'm going to go back to the hierarchy mode, give it a name. This is my 1-bit ALU. And that's that. So now it shows up in the diagram. Now I'm going to make a new circuit over here. This is a new object. I'm going to do add circuit. I'm going to give it a name, and this is going to be our full-fledged ALU. So I hit OK. And now I've got a blank space here. I've got a brand new blank environment. We're going to use that 1-bit ALU to make an 8-bit ALU. So I've got my 1-bit. I'm going to stick it here, right? So you can see it's the same diagram that we had just finished, but it acts exactly like the thing inside, right? This is the behavior that it's going to reflect, which is super cool. So go back to editing. That one is double click right there, and you can and we'll start wiring these up. So I'm going to need 8 of these guys, and I like to place them in such a way that I can copy them. So now I've got 8 of these guys, right? Now, These are all 1-bit inputs and 1-bit outputs. Now to combine them together so that we use a bus like we were using before, I want to use what's called in the wiring a splitter. So I'm going to take this guy, and what this is it takes a multiple input. Here it's already set for 2, the combined end of the splitter, so that it's already set for 2 bits, and splits them out, or it takes 2 bits and combines them together. So in this case, we're going to set this guy to have a fan out of 8 bits, and its bit width in is 8. And you can actually tell it which input, which bit wires to which bit in the data, which is cool. And you can even have more than one copy of the same thing. So bit 0 and bit 1 both are connected to input 1, which is cool. They're like redundant, right? So there's a little bus thing right there, which is neat. And we're going to use that when we get further in the design process. Oops, on top. And 1. There we go. Right. So I'm going to create one 8-bit input. So here I've got a regular input, but I want it to be, instead of 1 data bit, I want it to be 8 bits. And that gives me an 8-bit input. And this is my A value. Right? And I want to copy this and do the same thing with B. So I want to change this to B. Right? So now what we want to do is wire these up. Actually, I'm going to make it face down so it's a little easier to wire. So that's my A input. And this guy, this is my B input. And I'm staggering them so that when I run the wires down, they don't collide with each other. Right? So here I'm going to run my A's. I've run all of my A wires here, you can see, to all my 8 registers. And now I'm going to start running my B's. So now I've run all of my B wires, you can see here. Every A has its own A and B based on the values. And now we need to start up the ALUs to each other. So here we've got our CINs, connected all of my C outs to C, those quite yet. And then we've got our op operation. So we want to make our op, remember, is a 3-bit input, and it controls what operation the ALU performs. So we want all the 1-bit ALUs to do the same thing. So I'm going to put down a new input, make it face down, change its data bits to 3, and that gives us our input. And we're just going to run these to all the ALUs, the same one to every single ALU. So now we've run the operation bits to every single ALU, you can see there. And now our outputs are starting to look good, which is awesome. And we also want to make sure we name this. So this is also called op, and I like it to go on the north, which is cool. And then we've got our sub bit. Now our sub should be our subtract, right? And our sub, it's going to be the same for all of them. So we've got a new input, and we're going to make that a top one too, because that's a control bit. I'm going to call it sub. Should be on the north. And we're going to connect those all to all the ALUs too. Alright, so it's going to go to every single one. So now the sub is connected to every single ALU once again. But at the very top, we need this CIN to be connected to something. And notice that, remember that when we assert sub, we also want to assert CIN because we're carrying in that least significant one. So this is our least significant ALU, which gives us everything we need to do, right? Now, for the less than operator, we have a carry in, we have an input here at the bottom, but these guys all want to be, should all be set to 0 for the less.
Thầy
And
ơi,
actually what we're going to do is we're going to carry this set
thầy ơi, bài này hôm nọ
number,
mình học rồi ạ.
or this set input, all the way to the top here, and take it into the less than. And all the rest of them are, we're going to leave the other sets unconnected, and all the rest of these less thans should be connected to 0. Now, to do that, we've got a constant object, and this constant allows us to set a constant value. I just changed the value to 0 to all the objects that we want. So here it's a constant 0, and I'm going to connect every single one of the unconnected less thans, besides that very last one, to the so now that 0 is connected to the less thans except for the least significant bit, and this is going to allow us to do our set less than, so that when we do less than, we take the subtraction, we subtract b from a, and if a is less than b, then it'll be negative, which sets the most significant bit, and that will set the less than operator here to we'll set the less than input on this one to 1, which allows us to copy that into a register. So this executes our set less than operation, which is really cool. So now we've got all of the inputs and outputs connected for this thing, except for our results. So we need to pull these results into an 8-bit thing as well. So what we're going to do is we're going to copy one of these again, and to do a multiple copy, you can drag over, and you can see they turn blue. That's our that's when we know we've selected them. Or you can select and then hit Shift, not Control, to do a multiple select. And I hit copy and then paste, and I can pull it. Oops, not that one. I can pull it over here. I'm going to flip this all around so that it works a little bit better in this case. So here I've got my 0, I'm going to flip the B around, and I'm going to make this my R for the outside, and I want it to be on the east. Pull it over here, and it's all fancy connected. Oh, and I want it to be an output, not an input, so I can actually change that here in the select. I want it to be an out. Awesome. And then I just basically, we're going to connect it to all of the result outputs here. So I've got a result, and I just go through and connect all of those up to that bit. And you can see that was the least significant bit that I connected there, and these X's means that they're disconnected or they're don't cares. So now I've got all my result bits from the 1-bit ALUs combined together, and you can see we've got a really basic ALU here. We've got basically right now it's set to do an and you can see that it only ands on that bit if there's a bit in both of those positions. I think 1, 0 was add, so there I've got it adding together. You can see it ends up being 1, 1, 0. If we do the same thing and then subtract, then it's a subtraction. You can see I'm subtracting what is this, 5 from 1, which gives me -4 in binary, which is super cool. And stuff like that. So that's the really basic ALU. But we've got one more thing. We've got a set less than operation, an equal to operation for branches. So when we branch on equal, we want to make sure that that works. And to do that, we need a signal for 0 because we're looking at differences. So if they're equal, when we subtract them, we'll get 0. So we want to be able to detect when all of the results are 0. And to do that, we basically just take a look at our gates again, and we take a really big NOR. The width is 1, but the number of inputs is 8. So it's an OR, or a NOR, with 8 inputs. And I'm going to connect each of these inputs to one of these guys here. So now I've got my NOR connected to all of the outputs of the thing, and that gives me a little flag here that tells me whether or not the outputs are 0. So I want a simple 1-bit operation, and this is, I'm going to call this my 0 flag. Awesome. So So that's our complete ALU, and we can see here if we test it, and we've got, say, the same thing in both registers. We're doing an addition, so that one ends up being totally wrong. But if we make it subtraction, the same thing subtracted from itself is 0, and we get the same output there, which is cool. So this is how we'll do our equal test. So we'll do subtract, and if they're equal, it'll be 0, and that'll be our little flag that we'll use for branches and everything. So that's our basic operations in Logisim. Now, what I'd like you guys to do is to set up this ALU object. So go back into the editor and set up this ALU object all nice and pretty so that we can use it in designs in class. And I'm going to give you some supporting hardware that we're going to use later. Okay? Hope you liked this little video, and I'll see you guys in class.
Alright, so what you're looking at here is a program called Logisim. It stands for Logic Simulator, most likely, or something like that, because it's a program where you make logic circuits. Now, if I had to describe what a logic circuit is it's basically an electronic circuit made up of things like transistors that performs logic on binary signals. And a binary signal is a signal that has one of two states, either on or off. Now I've got some examples down here of some logic circuits, specifically some logic gates, which are circuits that do specific operations. They do specific things. And I've got the logic gates right here. Over here on the left, I have toggle switches, where each of these little boxes is a button. Each one of these circles is an LED representing what the state of that toggle is. And then these LEDs over here show what the output of each of the logic gates are. These green lines right here are wires, with dark green being off and light green being on. So this is an AND gate, and it's called that because let's say these two things are inputs A and B, and this is the output. The output is on only if A and B are on. So if I go and I turn A on, nothing happens. If I turn just B on, then nothing happens. But if I turn A and B on, then the output is on. Now another way to refer to this instead of saying on or off is true or false, where false is off and true is on. This is an OR gate, and it's called that because it'll be on or true if either A or B are true. So I can turn this one on, this A input, and it's on. I can turn this B input on, and the output's on. And I can also turn both of them on, and it'll be on. This is a NOT gate. It only takes one input, and it basically inverts it. As you can see, the input is off, or false, and the output is true. So if I turn the input on, then the output turns off. And, okay, it's not turning off. I don't know why it turns the simulation off when I do that. Sometimes. That's weird. Anyway, you can make all sorts of different circuits that do all sorts of interesting things with combinations of these various logic gates. And this certainly doesn't look like logic gates because it's not. It's the very top level. Inside each one of these little boxes is a whole array of logic circuits. As you can see, this one's little tooltip indicates that it's a ZE 8-bit microprocessor. ZE standing for Xenon, because I made it. And this right here is a 32 by 32 LED matrix, and it's all off right now. And this right here is a ZE 32 by 32 display controller. It basically controls this display. You can see that it's only got a few inputs, yet it controls this whole thing, and I'll get to how stuff like that works later. This right here is called a ROM. If you don't remember what a ROM is, it stands for read-only memory, or read-only memory. And it's memory that can only be read. So, examples of something like ROMs would be, even though you can burn some DVDs, so those are actually called DVD.
Rồi lớp đã sẵn sàng chưa nhỉ? Rồi để cho chúng ta một cái khoảng thời gian 2 tuần thì các trưởng xem phân công mọi người báo cáo xem là có những cái thành quả gì trong 2 tuần qua.
Dạ vâng ạ.
Có bao nhiêu bạn đã cài hết đầy đủ phần mềm và công cụ để làm việc không? Hôm qua thì tôi thấy có một số phản hồi, có nhiều bạn vẫn còn ngơ ngác, còn không hiểu cái môn này nó làm cái gì, chỉ đôi khi chả biết học điện tử số nó làm gì, vi xử lý như thế nào, vi xử lý đúng không ạ? Chả biết khái niệm vi xử lý. Nên có một bạn gửi tôi một cái mạch, hỏi thầy ơi đây là mạch của em, môn này có được không? Thế thì tình hình của chúng ta là sẽ vào khoảng 14 tháng 11 lịch thì chúng ta để ý cô Thủy thông báo chúng ta sẽ thi online và thi vấn đáp, mỗi bạn có từ 10 đến 15 phút, có bạn nhanh thì chắc chỉ 1-2 phút, không làm được gì đúng không ạ? Thi online thì yêu cầu là chúng ta về mặt kỹ năng nữa. Thì giống như ít nhất là phải giống như cái bài đầu tiên đấy, ta vẽ một cái bộ ALU 8 bit trên phần mềm Logic Sim, thì ít nhất là chúng ta phải nắm được một cái công cụ đó là Logic Sim, và chúng ta phải vẽ được, phải thiết kế và mô phỏng được một cái phần thành phần, một cái khối nằm trong cái máy tính đúng không ạ? Còn máy tính của chúng ta là máy tính 8 bit hay 16 bit đấy thì tùy đúng không ạ? Chỉ là 32 bit cũng được, bạn nào mà đây ta vẽ thì con số 0 thì vẽ từ giấy trắng đi lên, bạn nhìn thấy đấy, người ta vẽ đấy. Nên là chúng ta phải trang bị thứ nhất là cái kỹ năng để chúng ta thực hiện theo cái design này, đấy là về kiến thức, phải nắm vững được kiến thức về nguyên lý, cái đồ nguyên lý, chức năng hoạt động và cái khối trong cái máy tính đúng không? Thì như cái video đầu tiên là tôi nhắc lại đó, video đấy chúng ta đã được xem đi xem lại rồi. Video đấy là vé để video đấy thực hiện thiết kế một cái bộ ALU cho cái máy tính MIP đúng không ạ? Gọi là million instruction, nó là hàng triệu các tính trên giây.